Okay, we'll introduce Poynting's vector next. The direction the EM radiation propagates is given by the average value of Poynting's vector, and it's equal to 1 over mu 0 times E cross B, where E is, of course, your electric field and your B is your magnetic field. It's a cross product, so it's always perpendicular to both. The direction of propagation is then also always perpendicular to your electric field and to your magnetic field. The reason why we end up having the mu 0 there, because the direction wouldn't need it, but this is a particularly useful formulation for it because it ends up also describing the rate at which energy is being moved from one location to another. And in particular, the power flux is the flux of the Poynting's vector. So it's how much energy per unit time passes through a particular area. So Poynting's vector has units of joules per square meter per second, or watts per square meter is also common. There's no special name for either one of those, so you use and watts per square meter is a little bit more common. So we also then define the intensity of the light as being the magnitude of the RMS value of your Poynting's vector. So then that simplifies to 1 over mu 0 ERMS times BRMS. So it's equal to C over mu 0 times your RMS magnetic field squared. It's also 1 over C mu 0 your electric field RMS squared. So I gave an example. We suppose we've got a laser source that's 250 milliwatts. The diameter of the light is 1.5 millimeters. So we want to find the average RMS value for your electric and magnetic fields. So to find your intensity, it's how much power is delivered per area. So it's the number of watts divided by the area there. And notice I gave diameter, so it's half the diameter is the radius. So your intensity is given as 141,000 watts per square meter. Then use that formula that we just derived that allows you to calculate your RMS electric field will be 7,300 newtons per coulomb. And if you divide by the speed of light, you get 24.4 microtesla as your RMS magnetic field. So that gives you numbers that would be associated with that. That intensity is about 100 times greater than the intensity of maximal sunlight, direct sunlight. All right, so we can also use this to describe how much energy is contained in a region of space by light, and that's I gave in your supplemental stuff a derivation for this for a couple of special cases. It is generally true that the energy density, the amount of energy stored, if you have electric field in a region, it is 1/2 epsilon 0 E squared. The amount of energy stored in a magnetic field is 1 over 2 mu 0 magnetic field squared. Again, it's not obvious that that's true, but again, I gave you a couple of examples. The simplest ways to come up with those formulas is true in those cases, but it's true in all the other cases too. It turns out that your total energy density is your intensity divided by the speed of light, and that ends up being your epsilon 0 times your RMS electric field squared. It's equal to the square of your magnetic field RMS divided by mu 0. There's not the 1/2 there because there's equal amounts of energy in the electric field and the magnetic field. So your intensity is twice as much as the energy stored in either one. So I gave you then a calculation with that same example I gave before, that if it's 141,000 watts per square meter, that you end up having energy density of in 1 cubic meter of space. When that energy is flowing, you end up having 470 microjoules of energy, and 235 microjoules of it is due to your electric field, and 235 is due to the magnetic field. One other thing that happens with light is radiation pressure. So what pressure is, and I don't know how well your chemistry teachers describe this, particularly since you don't have momentum generally available to discuss in a chemistry course when you talk about pressure. What pressure is about is you have gas particles come in and whack the wall. So they'll whack the wall and bounce back. So when they do that, they transfer momentum to the wall. And so the amount of pressure is equal to the amount of momentum transferred per unit area per unit time. So if you end up taking your momentum divided by your area divided by time, that's kilogram meters per second. Divided by area, that's now kilograms per meter per second. You divide by time, it's kilograms per meter per second squared. You check your units. Newtons is kilogram meters per second squared, so you divide that by meter squared. So it's newtons per meter squared, which is probably how you were told to derive the idea of a Pascal. So that's what's happening there. So you have the same type of situation. It's the amount of energy that ends up being absorbed by the surface that it hits. So your radiation pressure is given by something between two expressions. One thing that can happen is the light can be absorbed. In that situation, it ends up having the amount of radiation pressure due to the momentum going to zero. So then it will end up turning out to be your intensity divided by the speed of light. If it reflects, then remember the momentum transfer is twice as much whenever it bounces back, because remember the speed has to be the speed of light. So that's not, so you're not going to lose any momentum magnitude. So you have the same amount of momentum magnitude going both ways. So the momentum being absorbed by the wall then is twice that, 2I over the speed of light. Most things are neither perfect absorbers nor perfect reflectors. So if you've ever heard of the concept of albedo, albedo is a number between 0 and 1. And if you take the albedo plus 1, you multiply that by I over C, and that's the amount of radiation pressure. So it's basically the albedo is the thing that goes from 0 whenever it's perfectly absorbed to 1 when it's perfectly reflected. So that ends up describing that range, and it describes what albedo means.